Okay, welcome to the 5th International Symposium on Multidisciplinary Studies and Innovative Technologies. My name is Emir Köksal. I'm a professor doctor in the Department of Mathematics at 19 Mayıs University. Welcome to this session. There are 7 presentations in this session. The duration of each presentation is 15 minutes. The first speaker is on the last one, Sangolius. The title of his talk is A Comparative Analysis on Term Weighting in Exam Question Classification.
Right. Thank you for the welcoming note. Okay, so let me bring up my screen. Okay, so over here is 2 p.m. right from Malaysia. Okay, good afternoon to you all. Okay, so the title of my presentation today is a comparative analysis on term weighting in exam question classification based on Bloom's taxonomy, right? So this is my name. I'm from Utah. These are my co-authors. Right. So I'll just give you an idea, right? What exactly question classification based on Bloom's taxonomy is, right? So before that, a brief explanation about text classification. So all these, the term weighting, right, have been used widely, right? Not only in text classification, right, in image processing and so forth, right? So this text classification, right, basically is to classify documents in general, right? And then of course we use supervised techniques like SVM, neural network, and so forth, right? So this question classification actually comes under the umbrella of text classification. So question classification, right, is even difficult in terms of pre-processing. Of course, we have a standard ways of cleaning for text classification, a standard way actually to convert, right, certain words to numerical measures, right? So that we have plenty, right, well defined. But when it comes to question classification, right, we have a different requirements because every in any, I think some of the universities, right, they have to set the exam questions, right, and then based on the Bloom's taxonomy, right? So Bloom's taxonomy, right, we have 6 levels like knowledge, comprehension, application, analysis, okay, and then evaluation, synthesis, right? So we set exam papers according to the difficulty level. So therefore, we have 6 levels. So here, when I talk about question classification, means is based on the Bloom's taxonomy. So all this while we have been doing on the manual basis, which means that when you set a question paper, then we need to label it, okay, whether it is actually knowledge level or whether it's evaluation or synthesis. So we need to do it manually, right? But when it comes to the machine learning, when we start applying the machine learning, right, so we don't need actually, right, human intervention actually, right? So we will give some data set to the machine learning, okay, with the questions and the labels, and then thereafter, right, in future, right, it will automatically, right, will classify, all right, for the new questions, right, what will be the label for the question, Bloom's taxonomy question, right? So that is about question classification based on Bloom's taxonomy, right? So we start using some techniques, machine learning, to automatically classify the labeling of exam questions. Okay, so what is the research motivation here? Since 2010, right, people actually have done a lot of studies around question classification based on Bloom's taxonomy, right? But so far, right, there is none, actually, I would say none, the research paper, right, that actually put together all the term weightings, right, in just one experiment, right? Detailed study, right, it's not there, right? So it's lacking. So that is the research motivation, term weighting. Okay, objective of the research to identify the appropriate term weighting technique for benchmarking of baseline purposes, right? Very commonly, right, when we talk about term weighting, we have 2 types. One is the unsupervised term weighting, the other one is supervised term weighting. So we actually started off with the unsupervised term weighting, like, you know, very popularly known as TF-IDF, right, term frequency, inverse document frequency. So that actually is a very like a de facto thing, very standard thing, okay? But in question classification based on Bloom's taxonomy, we are still using it. But there have been some researchers, right, that improved the TIDF. So we need to compare the TIDF against the improved ones, right? To ensure, right, we'll have a new baseline. So we don't want to compare the TIDF anymore, right? So for benchmarking purposes, so we need to come up with we need to have a benchmarking with the improved term weightings, right? So as we know that exam questions, right, we have, when you set exam questions, we have a string of words, and this string of words, right, consists of nouns, verbs, adjectives, right? So the important words will be verbs, right, compared to the nouns, right? So we give priority for the verbs. We need to give after that, followed by for the noun, after adjectives. So why we need to give priority for the verbs? Because the verbs actually determine the difficulty level, right? So therefore, right, the TIDF actually, right, does not give this kind of priority, right? So TIDF actually based on the distribution of words, that's all, right? So we don't actually give weight, okay, for the verb should be given higher weight, or for the noun should be given higher weight. No, it doesn't do like that, right? So that is why some researchers actually, right, have improved the TIDF in the context of Bloom's taxonomy, right? So this is the literature review, right? So I put it in a table form, right? This is a summary, right? So the category E, right? All these 1621, right? All these past researchers, so they actually have worked on the term weighting, feature selection, feature extraction, machine learning, right? So so the E category, right? The same researcher actually, right, in different papers, right? So this guy actually, right, have improved, right, the term weighting, right, over the TIDF by giving appropriate weights for the verbs, nouns, right? So these two papers, right? So ETIDF, TF, and the embedded. Okay. So the binary TF and TF IDF, right, is actually is studied in the previous, right? So this is the term weightings, improved term weightings for the Bloom's taxonomy, all right, question classification. Okay, so I did actually compare between binary TF, TIDF, EITIDF, and TF post IDF. So we do comparison. So methodology, data sets, 181 questions. All right. So this 181 questions actually taken from the previous researcher back in 2017. All right. So that it will be reliable. All right. So these questions have been already used before, right? So it's quite well distributed in terms of the labels, the knowledge, application, right? And then evaluation, right, is well distributed, so that it will not really affect the accuracy of machine learning, right? So that's meant by here, quite well distributed, the labels, right? Domain specific, because this question is actually related to the business area. Of course, in the future, right, I might actually try out with other domains, right? And then less similarity between questions. So whatever the questions that you have for 181, right, the similarity between one question with another is completely different. I mean, it's less similar, right? Very less similarity, right? So why I'm picking on this, because we really need to test, right, whether the term weighting, right, the comparison, right, really works or not, right? So that is why questions are actually, right, choose with very less similarity, right? So if you have like very high similarity, then, right, certain things, right, may be hidden, or maybe the term weighting really can't really test properly, right? So I made sure that every question, right, is unique in its own way, right? Okay, so this is the the flow, right? The question classification model, we call it, right? As usual, this one happens in other areas, well, text classification, right? We do the tokenization, normalization, lemmatization, and then feature extraction, term weighting, right? And then we feed into a machine learning, training, validating, and then we get the output, right? Classifier evaluation, right? So classification techniques, I use SVM, naive based. So if you ask me why I use SVM, SVM actually is de facto for question classification based on Bloom's taxonomy. All right, so we get a very good accuracy, right? SVM, and also the naive based, right? So metrics, what are the measurements that actually used to evaluate the output? So I use accuracy and F1 measures, right? So over here, I'm actually used K-fold cross validation now, right? 3 to 10. Why is it 3 to 10? Because to get more reliable figures, right? So I didn't actually really test with just 3 or 4, right? So I get the average, right, using K-fold cross validation. This is better than training and what you call splitting technique, right? Cross validation is better technique. Okay. So over here we have cross validation, right? 3 and starting up to the 10. So for every term weighting, right, you get accuracy F1, right? So I get the average. So this is like more reliable, right, compared to just like taking 3 or 4, right? So you get the average. So when you look at here, binary TF and TIDF, this is enhanced. This is TF post IDF, right? So these two things, right, E and TF, right, they have actually given different weights for the verbs and nouns, right, compared to TIDF. So TIDF is just a distribution of words, right? So for the last two, actually, right, given importance for verbs and nouns, right? So yeah, obviously, right, when you compare this SVM and the naive base, the SVM actually gives a better accuracy compared to the naive base. And we see that the last two, right, is certainly better than the TIDF, right? Better, right? So much better. And binary and TF, right, are not much difference, right? Because binary, right, because most of the time, right, in a particular question, right, the occurrence of a particular word is just only once. Hardly it will repeat, right, by itself. Right? Hardly it will repeat. So that is why the binary and TF, right, the accuracy, right, more or less the same, right? Not much difference. But when you compare TIDF against binary TF, of course, there are differences, right? Okay, so this one actually compares between classifiers, right? And obviously the naive base also, right, gives quite consistent results, right? When it comes to comparing the last two against the TIDF, right? So higher than the TIDF. And also I did another analysis. This is for normally when we do the term weighting testing, right? Evaluation. We want to see, right, how well, right, the words actually, right, the discriminating power, we call it, right? How well it can actually discriminate from one word to another word. So over here, right, I took just a question, state basic business activity perform revenue cycle, right? So can you see the difference, like TIDF, right? This compare the state, compare with this is noun, and this is actually, this is verb, this is noun, right? So we minus and see, right? Is it is it the value is larger than ETIDF or TF post IDF? So we want to see over here, we see, right, there's a large difference, right, between the verb and the noun, right? 4.70 and 2.88. Why? Because give importance for the verbs, right? So that is why it's actually well discriminated. So obviously for the E and TF, right, the verbs, when you compare with the nouns, right, the discrimination is higher, right? So the larger compared to TF, TF. So that is why the ETIDF and TF post IDF, right, gives a higher accuracy compared to TIDF, because simply it can actually discriminate very well, right? So you have a discriminating power, right? Okay, so this is the summary of findings. Generally, there's no significant difference between binary and TF, all right, TF. Okay, so the TF variant is more suitable for use exam question classification than TF2. So the TIDF, although, right, can outperform TF binary, right? So the former was outperformed by is the last two, right? So the using SVM classifier, ETIDF was performed. So it looks like TF post IDF, right, is better than ETIDF. Okay, so in conclusion, right, we can say that these both actually, right, are more effective than TIDF in increasing the accuracy of question classification based on Bloom's taxonomy. So this actually will set a clear direction, because in future work, right, very often, researchers, they will just use TIDF, right? They, I'm afraid they will not actually use this. They're right, by right, they're supposed to use this for benchmarking as well, all right? Because this is more relevant to the question classification based on Bloom's taxonomy compared to this, right? Of course, you can compare this, right? But also this need to be compared, right? So in future work, right, this should be compared as well, right? Okay. Okay, questions. So I guess that's all now, right? Thank you. This is my presentation, right?
Thank you very much for your presentation.
Yeah.
Is there any question, comment, or remark? No question. Thanks again for your presentation.
Thank you very much. Thank you very much.
Second speaker is Anurag Dasgupta. The title of the talk is Student Performance Evaluation of Distributed Algorithm Assignment in an Undergraduate Algorithm Course.
Okay, so let me share my screen. Okay, can you see my screen now?
Yes.
Okay, great. So yes, good morning, everybody. So the title of my presentation is Student Performance Evaluation of Distributed Algorithms Assignment in an Undergrad Algorithms Course. And I'm from Valdosta State University of Georgia, USA. So this is the basic outline of my talk today. Initially, I'll start with introduction, background, the methodology, and that will be followed by the results and conclusion. So as we all know, distributed computing is a field that has lately seen tremendous increase in interest. And that's the reason why we thought that in Valdosta State University, in our algorithms course, we will have some distributed algorithms components so that the undergrads can be exposed to the distributed computing early on. There is a separate course for parallel and distributed computing, but the students take that later. So this is like, we introduce the distributed algorithms as an in-class assignment for students in an undergraduate algorithms course. Now, for this research, the main focus was, the motivation was to find out whether having some prior knowledge about traditional algorithms help understand the distributed algorithms better. So before we introduce the distributed algorithms, we wanted to see like if the students already know the traditional algorithms, in those cases, whether it helps or not. And also like if they don't know or they don't have any prior knowledge, whether having suitable in-class examples help. So between prior knowledge and in-class examples, which one is more important? That's kind of motivated this work. So here's a little background of what we did. So the course, as I mentioned, is an algorithms course of the undergrads. The prerequisites for this course is the data structures course. And this study was done just last semester. So that's spring 2021. And there were 37 students enrolled in this course. But for this particular assignment, 35 students submitted the assignment. So the results were based on those 35 submissions. And points from the assignment contributed substantially towards the overall grade, that is to encourage and motivate the students to participate. So we have the traditional minimum spanning tree algorithms in our algorithms course, and students usually learn that at the very beginning of the semester. And by minimum spanning tree algorithm, so here the minimum spanning tree algorithms we teach for the traditional minimum spanning tree algorithms like the Prim's and the Kruskal's algorithm. But in this course, the students do not learn any traditional matching algorithms. So when we later in the course introduce the distributed version of these algorithms, we chose two self-stabilizing distributed algorithms, one with the self-stabilizing maximal matching, and the other one is a self-stabilizing spanning tree algorithm. So for the spanning tree, as you can see, the traditional algorithms, the students already know, just like Prim and Kruskal algorithm. But for the matching algorithms, they don't see any matching algorithm until this course. And also in algorithms, we, according to our syllabus, we don't have any matching algorithms the students are exposed to before they see the distributed algorithm. So this is kind of like these two algorithms, which I mentioned, are actually taken from some popular algorithms of distributed matching and distributed spanning tree. So in the original paper of the distributed maximal matching algorithm, there are no example in the paper, but the students did some in-class example. That means the instructor provided some in-class examples to the students. So this is like the original paper from where the algorithm is taken, as I mentioned that as a reference here. And for the distributed spanning tree algorithm, in the original paper, there is one example. So this is the paper cited here. Now, for this, we also have treated, because for the COVID, we had the hybrid mode of class going on at that time, at least, like the spring 2021 semester. So we could do, one group of students were told to study the algorithm on their own from the paper, but another group who was in class, for that group was exposed to the in-class examples that the instructor did in class. So here is from the student's perspective, like how things are, from their perspective, from their knowledge, this is what they are exposed to. So as you can see, for the distributed algorithms, for maximal matching, they were introduced for the first time, but spanning tree, they already know the traditional algorithms. So students were introduced for the first time, the distributed algorithms in both cases, but for the traditional algorithms, students were taught the prim and Kruskal, they don't have any prior knowledge of the matching algorithm. For the in-class examples, for maximal matching, few examples were done in class, but for the spanning tree, no example done for online students, they just studied on their own. But for the in-class students, some examples were done. And for other resources, like for both algorithms, actually, the resources are not easily available on the net. Obviously, those two papers, those are available to the students, but apart from them, no other examples are easily available. Even if they do Google search, there are very few examples to come by. And for the examples in the research papers from where the distributed algorithms were taught, as I already mentioned, for maximum matching, there was no example actually even in the original paper that they were given. But for the spanning tree, there was one example available, and the students who were taking the class online, they were asked to go through the example on their way, on their own, and if they have any questions, they were told to clarify the doubts from the instructor. So just a little bit of sidetracking, you might be wondering, what is this self-stabilizing algorithm? So self-stabilization is a concept of fault tolerance in distributed computing, and that was originally introduced by Dijkstra back in 1974. A self-stabilizing algorithm has two properties. One is known as the convergence property, one is known as the closure property. So the convergence property states that in a finite number of moves, even there is a fault in the system, in a finite number of moves, the system is going to come back to a legitimate configuration, and that is called the stabilization. And once it reaches the stabilization, it stays in that configuration unless any other fault hits the system, which is known as the closure property of the system. And this kind of system is very useful because of its nature, it can handle transient faults of any nature. Because even if you introduce a fault, according to the self-stabilizing algorithms, there are actions that will be taken so that after a finite number of moves, the system goes back to a legitimate configuration. So these two algorithms, the distributed algorithms that were introduced in class, are of this self-stabilizing nature. Now let's talk about the assignment. So the assignment that we are talking about, it consisted of 4 problems. And out of those 4 problems, the first 2 problems were where the students actually had to implement the 2 algorithms. So they studied the algorithms. For some cases, they have examples provided. And for some other cases, they don't have any examples provided. But the 2 problems, the first 2 problems required the students to implement the algorithms on a given graph and show how the stabilization is finally reached. And then the third question was an analysis question where they were asked to state the difference between the distributed and the traditional spanning tree algorithms, because they learned the traditional spanning tree algorithms earlier in the course. So they were asked to show the basic difference. They were asked to state the basic difference between the 2 different types of algorithms. And the last question was a reflection question. So where they, hello?
No, do A.
So for the last problem, it was a reflection problem where the students were asked that how helpful were those in-class examples, considering they never studied a matching algorithm before. So now let's take a look at the results and see what is the finding. So as I said, 35 students submitted the assignments. And we have this table where we kind of have the different scores for the different problems, different 4 problems. Just like we categorize them as greater than equal to 90%, how many students scored between 80 to 89%, 70 to 79%, and less than 70%. So the table has all the numbers, but let's take a look at the graph to find out the pictorial information. So the first problem in this graph is problem number 1 has to do with the distributed maximal matching, whereas the problem number 2 is the distributed spanning tree algorithm. So let's focus on them for a moment. And as we can see from the graph, that students perform better for the second problem in the score range of greater than equal to 90%. That means the second problem means the distributed spanning tree problem. So yes, for that problem, it seems in that category of greater than 90%, students perform better. But that's not the case, as you can see, for the other categories, because as we go from 80 to 89 or 70 to 79%, it is the problem 1, distributed maximal matching. That's where we have the better scores. And that's also like, I mean, if you think about less than 70%, that means in that range, it indicates that most students actually struggled with the second problem. So the second problem is the distributed spanning tree problem, even though they have prior knowledge to traditional spanning tree problems, but it seems like more students actually struggled with the second problem. So that obviously means that prior knowledge in traditional spanning tree is not leading to a better performance. Now, does that really mean like the in-class examples are more important? Because we can see from the previous that the prior knowledge is not really convincing us. But what about the in-class examples? Are they really helping or not? For better understanding of that, we did that other thing, like during one lecture, an in-class example of the distributed spanning tree algorithm was provided towards the end of the class time, only for the students present in class. So for the online students, because it was a hybrid class, for the online student, examples were not done, but for the in-class students, examples were done. And this is what the finding is. We find that 3 students who scored greater than equal to 90% for problem number 1 are actually the top students of the class. Like at the end of the semester, those 3 students received an A. But for problem number 2, where 9 students who scored greater than equal to 90%, it actually doesn't matter. The overall grade did not matter, because out of those 9 students, we have all sorts of grades there. Like there are A's, there are C's. And out of those 9 students, interestingly, 7 of those 9 students who scored greater than equal to 90% were actually present in person when we did the examples in class. So here is kind of like to see everything in a nutshell. If we find 4 different scenarios, right? Because we are talking about prior knowledge and in-class example. So we can have 4 combinations. Obviously, we are not interested in the first one, because this is the category no prior knowledge, no in-class example. But if you look at the other categories, it seems like that where they have prior knowledge and where also the in-class example was done, that is the case where we had the best performance, which is denoted by this green portion, because that's the distributed spanning tree algorithm. They have some prior knowledge of spanning tree algorithms. And also this is the group which was in class. And that's the group of students who did the best now at all, are where they have the prior knowledge, but there is still no in-class group, which the distributed spanning tree online algorithm, I mean the online group in the hybrid mode. And there, as we say, like almost half the students scored less than 70%. And just out of 2 students of those 9 students who were not in class, they only received that very good score. So this is obviously the group which did not do good at all. This is like the worst among these 3 groups. And somewhere in the middle is the group where they had no prior knowledge, but still they were exposed to some in-class examples. So this is what the distributed maximal matching, because in that case, both online and in-class groups, they received examples. Like even if it's a hybrid mode, but they provided the examples were provided to both groups. And that's where the performance is somewhere in the middle. So the findings were more emphasized by the reflection question, because in the reflection question, we asked how helpful were the in-class examples, considering they never studied the matching algorithm before. And this is just one of the many responses we got. As you can see, the student is claiming that these examples were very useful, and considering that there are not many resources available on the internet, it was the most helpful thing regarding the assignment. So in conclusion, I would say that doing in-class examples proved to be the quite effective method, which is supported by the results and the reflections. Students without prior knowledge but with exposure to in-class examples perform better than the students with prior knowledge but no exposure to in-class examples. And that kind of tells us that suitable in-class examples is of critical importance and should be emphasized more for effective student learning. It's more important compared to whether they have prior knowledge or not. So if you do more examples in class, suitable examples, that is what sticks to the students more. So I think, yeah, that's my presentation. If you have any questions.
Thank you very much for your presentation. Any question, comments, or remark? No. Thanks again for your presentation.
Thank you.
Next speaker is Asad Turhan. The title of the talk is Improvement in Handwritten Character Recognition by Using NN. Asad, present or absent?
Sorry, I think I'm the next on the list.
Yes, you are the next.
Cross-cultural usability testing, right?
So Asad is absent. Okay. Next speaker is Zvezdan Selmanovic. The title of the talk is Cross-Cultural Usability Testing of MOOC Platform. Okay.
Okay. Can you see my screen?
Yes. Yes.
Okay, so the topic of our study is cross-cultural usability testing of massive online open course platform, which is Udemy in our case. And I will talk about the aims of this study, the research design, participants that participated in this study, and the procedure we follow. And I will talk about the results in the end. So this study aims to perform usability evaluation of the Udemy website with 10 undergraduate and postgraduate students from different cultures coming from different continents. And the most important thing there is that they are coming from different cultures. So we are able to perform the cross-cultural usability testing. And participants were assigned 5 tasks, and those tasks were measured, and we got the quantitative results as success rate and time needed to perform each task. And in the end, participants were asked to fill a VROOM3 questionnaire, which is a website analysis and measurement inventory. The research design we have followed is mixed, so it means that we have used user testing and VROOM3 questionnaire in the end. So participants were asked to complete the pre-test and post-test questionnaires and perform 5 tasks on the Udemy platform, and the results were recorded. So the variables on this research are task success rate as a measure of effectiveness of interaction, time on task as a measure of efficiency of interaction, and questionnaire about usability in the end. So participants in this study were users of Udemy coming from different cultural backgrounds. So the pretest questionnaire they have filled in is giving information, giving their demographic information, age, gender, education, and apart from that, we have looked into the Hofstede's cultural dimensions of their countries, which are power distance, individualism, masculinity, uncertainty, avoidance, and long-term orientation, in order to compare results from VROOM3 questionnaire and look them through these Hofstede's cultural dimensions in the end. So the procedure was conducted in 3 stages. The first stage I already mentioned that participants gave their demographic information. In the second room, the participants were performing the predefined tasks created for this experiment in the quiet room, and after that, users were given a questionnaire to fill in and determine their satisfaction. VROOM3 questionnaire consists of 20 questions, and in order to assess usability, questions are related to 5 dimensions, which are attractiveness, controllability, efficiency, helpfulness, and learnability. And participants can rate this from 1 to 5, from strongly disagree to strongly agree. Tasks that were given to participants were 5 tasks which had to be performed on the Udemy website, specifically on this course, the Complete TOEFL IBT Success Group by Maria Gurieva. And the following tasks were given to participants: had to find the course, to find and play a specific video, to find question and answer sections, to find the quiz in the given course, and to find and download specific file. And time needed to perform each task was measured for each participant, and these were compared to Hofstede's cultural dimensions. After performing these tasks, participants were provided the VROOM3 questionnaire. So here on this slide, we can see the task completion time for each participant and for each task, and taking into consideration that all participants used Udemy before, time needed to perform as task longer than 60 seconds is considered long. On this slide, we can see the success rate. So most of the participants were successful in the given tasks, with some of them having troubles and some of them performed unsuccessful. And in the end, here are the results of user satisfaction survey from VROOM3 questionnaire, and we can see that participants generally rated website as positive, with helpfulness having the highest score and global usability score being 68.7. And on the next slide, we will look through results of each of the dimensions of the Hofstede's cultural of the dimensions that VROOM3 questionnaire is giving us result about. So in order to know more about the attractiveness of the website, participants gave answers to these questions. In order to assess controllability, these questions were asked to whether is it difficult to move around the website, or is the participant in the control when on website, and so on. About the efficiency, participants answer questions about how quickly they can find something on website. Is website too slow? Are they feeling efficient when using website? When giving answers about helpfulness, they were talking about whether the website seems logical. Can they easily find what they are looking for? And when it comes to learnability, they were assessing these questions. And in the end, the results from the VROOM questionnaire were looked through the hosted cultural dimensions. And after analyzing different groups that scored high and low on hosted cultural dimension of power distance, we couldn't see any significance difference. When looking into individualism versus collectivism and the VROOM questionnaire, we can see that participants coming from cultures who score high on individualism scale rated website as having high controllability and learnability, meaning that participants in this group found it more easily to navigate through website and that everything is easy to understand from the start. When it comes to masculinity versus femininity, participants coming from masculine societies scored higher on attractiveness, controllability, and learnability, with learnability having the largest difference. And efficiency and helpfulness were rated higher among participants coming from more feminine societies. When it comes to uncertainty avoidance, it can be concluded that there is no significant difference and both groups scored high. And the last dimension is long-term orientation. And here also we can see that there is no significant difference, but still participants belonging to culture with short-term orientation rank website as more appealing. And we can come to conclusion after this that the results of this VROOM questionnaire, when looked through hosted cultural dimensions, we can see that there is no significant difference between the groups in five cultural dimensions. But it is important to mention that this study was performed with a limited number of participants, specifically 10, and it was not possible to identify intercultural difference because results were not very distinct, and it would be more appropriate to find a larger group of more diverse participants and perform the study again in order to gain better insights about cross-cultural difference. And that would be it. Can you hear me?
Yes. Any question, comment, or remark? No question. Thank you very much for your presentation.
Thank you.
Next two presentations will be given by Falana William. The title of the first talk is Effect of Multimodal Imaging on COVID-19 and Lung Cancer Classification by Deep Learning. And the second talk is Deep Learning Classification of COVID-19, Pneumonia, and Lung Cancer on Chest Radiographs.
Thank you very much. Good morning to everyone. Firstly, I want to thank everyone that's present here today for this opportunity. And our topic today is effects of multimodal imaging on COVID-19 and lung cancer. So we are basically trying to go into the goals of the paper. We're going to see COVID-19 an overview, lung cancer an overview, and medical imaging. Then we're going to move to the methods that we used and data sets that we use and performance and evaluation that we deducted from our research, and then we're going to conclude this paper. So firstly, we know that deep learning is an aspect of machine learning that has been used in several different applications, especially in the medical field. And we have seen, if we have gone through papers and we have seen different applications, to different diseases. And then we decided that, okay, let's also apply it to some medical problems that nothing has really been done about. And then we decided to investigate the multimodal effect of deep learning, of classification on COVID-19 and lung cancer CT and X-ray scan, and to know maybe there's going to be any changes. Maybe it's going to improve the classification, or it's not going to be, or it's not going to result to anything. So that's what we wanted to look into, and also want to see if the planning can distinguish between COVID-19 and lung cancer, both CT and X-ray. So COVID-19 overview. Firstly, we know that COVID-19 is an infectious disease that's emanated from China, one specifically, and then we know that it's a viral disease and is highly infectious. We also know that it's a respiratory disease that attacks the lung region, and we know that early diagnosis of this disease can increase the chances of survival of such patient. The same thing goes with lung cancer. Lung cancer belongs to also one of the leading causes of death in the world today. Lung cancer is also a respiratory disease that attacks the lung region as well as COVID-19. And warning symptoms also includes shortness of breath, coughing up blood, and some other things like that. Then early detection also could increase the chances of the patient surviving. So actually, what motivated us to work on this was, if we take a deep look at both structures of the images, we can see clearly that the COVID-19 CT and X-ray, they have the same image structure. So it's difficult for a radiographer to be able to distinguish which one is lung cancer, which one is COVID-19. So that's why we are trying to create a deep learning classification so that it can be applied in the automation of detection of COVID-19 and lung cancer. So now what did we do? We did pre-processing and then classification using deep learning. So the pre-processing, we use data augmentation, which, because of the limited amount of images that are available, especially in lung cancer images. So we decided to augment the image we got. And so we did that by rotating at different angles, and also the light intensity on those images, we reduce some, we increase some to generate 4 different images for each image we had. And also we use AlexNet to do the classification, and the framework we use is MATLAB to do the classification. So clearly our data set was gotten from images available on the internet, and we got CT scans and X-ray scans, and we're able to train and test. And the ratio of our training to test is 70 to 30. So we splitted the image into 70-30, training for 70, then testing for 30%. So this is the image augmentation. We can see that we got, for each image, we were able to reproduce 5 similar images through data augmentation. And so at the end of the result, we are able to get an AUC value of 1 for COVID-19 and lung cancer, because we investigated 3 different scenarios. We saw COVID-19 and lung cancer CT scans. We wanted to know how well they do, and COVID-19 and lung cancer X-ray, we wanted to know how well they do also. And then the multimodal classification, which means that we classify COVID-19 mixture of both CT and X-ray scan, and lung cancer CT and X-ray scan. So we mix them up together and try to classify them and see if there will be really much effect on the classification. And we clearly see that there was no really much effect of the multimodal classification according to the results, because the accuracy was close to that of classification of ordinary X-ray scan, and was also close to COVID-19 the CT scans classification, and the sensitivity as well and the specificity. So there was really no much effect of the multimodal classification on the system. So our confusion matrix from our test results for COVID-19 and lung cancer, we tested 168 images, and we can see that this AlexNet was able to classify the 168 images correctly. The true positive there was 168, and then the false positive was 0, and then the false negative was also 0, and then the true negative was 168. So the classification was done rightly. That's why we had an accuracy of 1, and we had sensitivity and specificity of 1 in such instance. And also the COVID-19 and lung cancer X-ray classification, we can see that our true positive was 43, and our false positive was 0 because it's classified the COVID-19 X-ray correctly. Then the lung cancer, we had false negative of 5, and then true negative of 48 from the classification. And so there was 5 images that were wrongly classified, which affected the specificity, the sensitivity of which affected the sensitivity. And also for the multimodal classification, we can clearly see from there that from the COVID-19 CT mixture with mixed with X-ray, we got a true positive of 97, then a false positive of 8, then a false negative of 0, and a true negative of 89. So from the classification, and which really didn't, looking at this confusion matrix, we can clearly see that there was really no much effect of the multimodal classification in improving the results or giving us a better result. And also this is the ROC curve for the classification. We can clearly see COVID-19 and lung cancer. It was a perfect graph, and the AUC value was 1, and there was, due to the errors in COVID-19 and lung cancer history classification and COVID-19 and lung cancer, the multimodal classification, there was some variation on the graph which affected the AUC value, but there was no really significant impact of that on the AUC value, because the AUC value was 0.99 for both. So clearly, we were able to use deep learning architecture to distinguish between COVID-19 and lung cancer, and which we did that using 3 different scenarios, both the multimodal classification and also COVID-19 and lung cancer, the CT scans, and also COVID-19 and lung cancer X-ray scan. And then we were able to evaluate the performances of the system, of the classification, using the accuracy, the sensitivity, and the specificity, including the AUC value. And our findings, we discovered that AlexNet was able to distinguish between COVID-19 and lung cancer, and also
هذا المشوي
and also
كيف سرعة قراراتك دائما تتأخر.
also there was no significant improvement as a result of multimodal classification. So we may be asking that what's the application of this radiographers that takes this CT scan is going to be able to help them to, if an automated system like this is out, it's going to help them to be able to distinguish properly and help the spread of this disease like COVID-19, and they will be able to, it's going to be easier for them to do their job effectively with high accuracies, because we know that any mistakes in medical diagnosis can lead to severe consequences like death. So this is really going to help the radiographers. Thank you.
Excuse me, can you hear me?
Is there any question?
Yes, I have a question. Do you hear me?
Yes.
Yes.
Yes. I want to ask about, did you make any cross-fold validation for checking the bias? Is there any bias? Because if you use just one validation, the result will be high. Did you do like this? You don't
So,
mention in your presentation.
sorry, I didn't get your question clearly.
Meaning, if you're using one cross-validation for
Yes.
training the data, it will be biased. The result will be biased. How many cross-validation you do?
Actually, it's just one that we use in this classification.
Normally, one is not enough. Normally, one is not enough because the result will be higher. That meaning the result will be biased. This is the one cluster. Of using classification between CT scan and X-ray, because each image completely different to other, so that the result will be high also. Like if you don't mention it also.
I'm sorry, I'm finding it difficult to get to understand what you're saying. Sorry. The net. Can you please come again, sir?
I'm meaning what's the benefit for classification CT and X-ray? The X-ray data is completely different than CT scan data. Oh, the result will be high. This is the traditional thing. Everyone know these things. You need to make a classification between CT scan and also CT scan for COVID-19 and other types of diseases who relate for CT scan.
Yeah. Yes, because actually this is focused basically on CT for COVID-19 and lung cancer. So when we're trying to use only the CT and X-ray scan for determining the result for this, and that's why we did 3 different scenarios to come up with the result. That's why we didn't focus on only just a scenario. We had to do 3 other scenarios to see if it's going to get high. But if we use others also, I don't think it will basically affect the result. It will influence the result in another direction. It is going to influence the result towards the same directions.
Okay.
Yes.
I don't get there is what's the benefit for using classification between CT scan and X-ray?
No, because you see, if we use CT scan and X-ray scan, we use the classification between CT and X-ray scan. It's easy for the system because X-ray structures are totally different from CT structures, CT scan structures, and so
the result will be high. It's normally because the structure is completely different. The picture structure will be different, so the result will be high. This is the normal thing. I don't get the idea why you do like this. This is the second question. Here's the question: why use the Elixir? You can use the ResNet family, a lot of them. You can use DistNet, you can use GoogleNet, and whatever algorithm you can use. Why you use Elixir is
because there's some papers that have worked on ResNet classification and all that, so we don't want to do something that they have done already. So we couldn't find that of AlexNet. That's why we used AlexNet.
Okay.
Yes.
Thank you very much for your first talk. You can start your second talk.
Okay. So I'm trying to come up. Okay, can we see the screen? Yeah. So good morning to everyone. The second paper is deep learning classification of COVID-19 pneumonia and lung cancer on chest radiographs. So this one we are specifically focused on X-ray scan, X-ray scan, and the reason basically is because it's available in the hospitals. Most hospitals have X-ray scans, and it's easy for them to get, and access is cheaper compared to the CT scan. So the goal of this presentation, we're going to be seeing that on COVID-19 lung cancer, pneumonia, because we are using three different diseases in this case, in this instance, to verify if AlexNet also could distinguish between these three from their chest radiographs. And we're going to look at the methods and the data sets we use, and also the performance and evaluation, and then the conclusion. So firstly, we want to investigate how well deep learning architecture like AlexNet is able to distinguish between COVID-19, lung cancer, and pneumonia from their radiographs, that's chest radiographs. And firstly, we know the COVID-19, it's a viral disease. We know how infectious it is. And also, we know that it's a respiratory disease that attacks the chest region, the lungs region. And also, we know some symptoms of COVID-19, which we know that it causes tiredness, cough, and fever. And we know that early detection also can reduce the chances of it being spread and mitigate the disease itself. Also, lung cancer belongs also to, it also causes a lot of devastating effects on humans generally, and it's one of the leading cause of cancer, especially cancer-related disease. It's one of the leading cause of death in the world today. Lung cancer is also a respiratory disease that attacks the lungs region. Early warning symptoms may include coughing up of blood, shortness of breath, and early detection could increase the chances of survival. The same thing with pneumonia. Pneumonia also is viral and is a viral and transmittable disease like COVID-19. It spreads through the particles of liquid that is coughed into the air, and can another person can get infected from it, and it affects the lungs region as well. And early diagnosis of this can increase the chances of that person surviving. Radiographs, as I've said earlier, it's very easy for hospitals and test centers to be able to get, because it's more cheaper way compared to CT computed tomography scans. And so that's why we want to look into radiographs classification. And we know that chest radiograph expose the content around the area of the lungs region and the nearby structures, and it has the ability to expose affected areas and abnormal regions around the lungs. So what did we do? We use pre-processing in our paper, and then we do the classification using AlexNet. So pre-processing, we use data augmentation, which we use we try to flip the images at certain angles to generate more images for our classification. And also we reduce the light intensity on the images also, as well as part of the process of augmentation to increase the images. So for each images as well, we replicate 5 similar images to that. So this is the data set that we use. The ratio of the training to testing is 70 to 30%, 70 to 30. And our AUC value, we got an AUC value of 0.99 for COVID-19 and lung cancer classification, with an accuracy of 0.94, a sensitivity of 0.89, and specificity of 1. And if we look at these 3 results, because we had to do COVID-19 and lung cancer classification, we did COVID-19 and pneumonia classification, and we did lung cancer and pneumonia classification. So we wanted to see how well AlexNet could distinguish between them, and also the similarity, like how the difference between the accuracies, whether it's going to affect the accuracy that much or not. And from the confusion matrix, we can see the true positive. We had 43 out of tested images, 43, and there was no one that was wrong for the false positive. For the false negative, we have 5, and for the true negative, we have 48 that was correctly classified and 5 wrongly classified. That's for COVID-19 and lung cancer. Going to COVID-19 and pneumonia, we had 157 that were rightly classified as the true positive, and for the false positive we have 3, and the false negative we had 8, and the true negative we had 162. So 162 was right classified, then 8 wrongly, then 157 rightly, then 3 wrongly. And also for the lung cancer and pneumonia, we had 48 for true positive, and then 6 for false positive. Then for false negative, we had 0, and then for true negative, we had 42 from our classification. And so we, from the row curve that we deducted, we could see that for lung cancer and pneumonia, it was a perfect row curve, which had an area of 1, and for COVID-19 and lung cancer, there was some little, due to the little error affected the graph, and the area under the curve was 0.99 as well. And for looking at 0.99, and also for the row curve for COVID-19 and pneumonia as well. So we can see that there was some variation in the graph for the row curve for the true positive versus the false positive, and then it was also 0.99 from our deduction. And we clearly saw that deep learning also was able to classify and distinguish between the chest radiographs for these 3 images, and we did that by evaluating the performances according to the accuracy, the sensitivity, and the specificity, including the AUC value. And our findings show that deep learning architecture was able to distinguish between these 3 diseases, and also shows that deep learning algorithm successfully differentiated between COVID-19 and pneumonia with a very high accuracy compared to the 2 other classifications. And in terms of AUC results, the 3 had similar or close to similar results. Well, thank you. Is there any question? Is there any question?
Question, comments, or remark?
If I ask, he will close my sound. He make mute, so I don't ask.
Okay.
You can go ahead to ask.
You can ask.
Chair, if I ask, you make make mute for me. Why I asking?
No, you can ask, sir.
No.
We're all learning. Okay. Thank you.
Thank you very much for your presentation.
Thank you.
Last speaker of this session is Felix Olanrevaju Babaloa. The title of the talk is A Palm Vein Recognition Approach by Multiply Convolution Neural Network Models.
Hello, everyone. Good morning. Can you hear me?
Yes.
Okay. I hope you can see my screen as well. Can you see my screen?
Yes.
Oh. Good morning, everyone. My name is Felix, and I'll be presenting the topic, a palm vein recognition approach for multiple convolution neural network model. I work on this project with Professor Dr. Onsen Toga and Associate Professor Dr. Yichan Vitrim at the University of Eastern, at the Computer Engineering Department, Eastern Mediterranean University. So first I will start with the introduction, where we talk about what this is all about, and then the proposed method will be expatiated on in 3 phases, and then the experiment that was carried out and the result in 2 phases. Then finally the conclusion will follow. So we all know that biometric systems where physiological traits such as the face, palm print, and fingerprint, iris are now common commonly used technologies around the world for women authentication. This is also encouraged by technologies that are able to capture these traits. The images of these traits can be captured easily nowadays. So it has really motivated the use of these traits for human authentication. The usage of hand vein has also become very popular. And this can be generally in 4 different ways. We can get from the palm, from the back of the hand, from the finger, or from the wrist. Yeah, and because veins are very stable in humans, they do not change from time to time, and it is very hard for you to present fake vein image to the system during the data capture process. Then it has an automatic spoof detection feature. So, and also on your hand, when you're using palm for your traits for human authentication, there is no occlusion. That is, there is no interference by clothes, cosmetics, or things like wristwatch will not be on the hand. So, and it's also very easy to use, to ask people to use this method, because people are usually more eager to use their hand for authentication, especially if the system can be built in such a way that it is contactless and they have no worries about contacting diseases from using such system. So in this paper, we have combined 3 convolutional neural network models, which is VGG16, VGG19, and AlexNet, to build a pattern recognition system. Here is the structure of the proposed method. This structure, I can divide them simply into 3 parts. The first part is the pre-processing stage, which is basically where the region of interest is cropped. As we will see, when images for recognition are captured, they are always captured along with other parts of the hand that are not needed for authentication. So, for example, you may have the hand, the fingers, or the upper part of the hand. So these parts are cropped out to get the region of interest. Then the 3 CNN models that we use, they are here. Each of these models will be explained briefly in the next slide. Then lastly, we have the fusion of this model to get the final decision of the proposed system. So the first model is the VGG19 architecture, which is a very popular CNN model. It has 16 convolution layers, as we see in this structure, but it is only 5 layers, as the convolution layers are put together. Like you see in the first layer, we have 2 convolution layers, and the second 2, then 3 in the last 3 layers. However, in this study, we propose that the number of filters in each of these layers, convolution layers, should be reduced drastically to increase the training time of this system. So we reduce the filters in each convolution layer, as we see in this table. So, for example, in the first layer, the 2 convolution layers have 64 filters, but in here, in our proposed one, we use 32 layers, which is just 50%. And we do the same for all the layers, as you see in this table. So we reduce to as much as 75% in the 3rd, 4th, and 5th layer. Sorry, 4th and 5th layer. The second model is the VGG19. It's very similar to VGG16. The only difference is in the number of convolution layer in layer 3, 4, and 5, where one convolution layer has been added to each of these layers. And similarly, again, we reduce the number of filters in each of the convolution layers. This table is exactly the same as we have in the previous model, VGG16. Lastly, the AlexNet architecture is shown here. This also has 5 layers, but the difference is that we have just one convolution in each convolution layer in each of these layers. And the number of filters is also reduced in this case, as we see in this table, also from 75% to 66%. So as this table gives a full detail of how we have reduced the number of filters in each of the layers. Additionally, if you see in the original model of AlexNet, we have different filter size, like 11 by 11 in this case of first layer, and the second layer 5 by 5. So in our proposed model, we have used only 3 by 3 throughout to be consistent, especially because in the first 2 models, we also used 3 by 3 models throughout. And of course, one thing I forgot to mention is that after each of these models, we have the max pool layer, which is kept to be the same throughout the 3 models as well. And we have the fully connected layer that ends each of these models. Then after the models, we have the decision level friction of the result we will get from each of the models. So we will have 3 decisions, one from each of the models, like I mentioned. So the weight is assigned to the result accordingly. So we have 1 for correct recognition and 0 for incorrect recognition. So which means that for each sample, we have the possibility of having 0 to 4. I mean 0 to 3. That is 4 possible answers. So for 2 and 3, we will be given true recognition, and 0 and 1 will be false recognition. This is the model of the decision level fusion. Okay. Now, to test this model, we have used 3 databases. The first one is the FYO database, which is a multi-trait handling database. It has DOSA, PAM, and wrist vein patterns. So the dataset was acquired from 60 volunteers in 2 separate sections. So, but since our focus is on PAM vein in this experiment, we have used only PAM from this database. The second one is the PUT vein database, which consists of wrist vein and PAM vein dataset. Again, we have used only PAM vein from this database as well. The database was taken from 50 volunteers in this case, but because they took from both hands, a total of 100 classes or 100 entities exist in this database. The third dataset was from Vera, which consists of 2,200 images. The number of volunteers for this one was 110, taken in 2 sections as well. Now, like my previous speaker spoke about how it is important for us to use a large number of samples in training, in deep learning. This also applied to our work here, because we needed to augment our data to increase the number of samples so that it will be training can be done properly. So for this, we use Keras data generator, which of course generates more images by altering the input images by rotation, share, width, shift, height, zoom, and brightness. So consequently, when we use this data augmentation algorithm, we increase the number of samples in our data set. So we got this number of images per data set, and they are distributed to training set and test set. As we see, for example, in FYO, we have 5,760 for training and 640 for testing. The distribution of the rest is given here. Of course, we note that we have to then do this as many times to cover all of them, to cover all the samples in the data set. So that all samples can be used for training and for testing. But because of time, we only did this twice. So not all samples were used for testing and training, but only about 20% was used for testing at the end, and the rest was used for training. So the experimental results obviously shows that the reduction in number of features will reduce the computation time drastically, as we got an approximation of approximately 450% reduction in time for training when we use our modified model. The training time is given here. So we see the original one for VGG16 and then the modified one. We did this for all three of the models. And as you can see, for example, if you look at the first one here, you see that the time, we have 6 digits. This is in seconds. It's 6 digits compared to just 5 digits. So if you divide them, you see that we have approximately 450% reduction in time, in training time, when you use the model that we propose. Now, the result is also very good compared to the original one. So approximately we have average of 96% accuracy across all the experiments that we did, even with using reduced features, which drastically reduced the amount of time needed for training. Also, we then propose to combine them, as I spoke about in the decision level fusion. Then the final proposed method gave us very good results, from 99.06% accuracy with the FYO dataset, and 99.83 and 99.26% accuracy in Qt and Vera datasets respectively. And we can see more detail in the table below. So in conclusion, the study introduces a palm vein recognition approach with the fusion of 3 deep learning algorithms. The study proposed a comparison of the study proposed the study compared the efficiency of the 3 models that we use, and then we proposed using fewer number of filters in each convolution layer in all the models, and then use a decision level fusion to bring the decision of the 3 models together for a stronger human notification system. And as we see, we have good results, good accuracy across the 3 databases that we use. Thank you very much for listening. This is the end of my presentation. Your questions. Thank you.
Is there any question, comments, remark? No question. Thank you very much for your presentation. Thanks to all participants to attend this session. So amending of this session.